For today's agenda, presentation 3, we'll have the system architecture and the control framework. So let's get going with the system architecture. We'll have a layer 0, which will be the hardware layer. Our microcontroller will be the ATMEGA 328P. In top of the layer 0, we'll have a layer 1, which is the microcontroller framework. The microcontroller framework will allow us to access all the registers in the microcontroller. And as I'll explain later, those registers enable us to control functionality and also configure the microcontroller. In top of that, we'll have a layer 2. A layer 2 will contain all the frameworks needed to ensure that the microcontroller functionality works correctly. So for example, we have the internal interrupts, external interrupts, I/O ports, UART framework, SPI framework, I2C framework, analog to digital converter, and finally the comparator framework. In top of layer 2, we'll have a layer 3. The layer 3 will contain a number of sensors that is going to ensure that we get to exercise all the functionality defined in layer 2. So we'll have displays, Wi-Fi, SD cards, servo motor, inertial systems, joysticks, a rotary encoder, potentiometers, RFID, relays, wireless transceiver, and also IR transceivers. We'll have temperature, humidity sensors, sound and motion detector, and finally DC motor. Now on top of layer 3, we'll have a layer 4. The layer 4 is going to be the Internet of Things. So we exercise in layer 3 all the sensors, and then in layer 4 we can transmit all that data through the internet. So we can see what's going on, and we can also control things through the internet. So let's get going with the control framework. As I noted, the microcontroller functionality is configured and controlled by manipulating 8-bit registers. The control framework will contain all code needed to access all microcontroller registers. So let's look at our approach. This is the data sheet for the ATMEGA 328P microcontroller. The document is organized around the microcontroller functionality. For example, we can see here the interrupts, external interrupts, timers, and so on. Now, each section contains a subsection titled Register Description. For example, if we go to the SPI peripherals, we can see that there is the register description subsection. Now, by accessing this subsection, we can get the register address. For example, in this case would be 4C hex. Also, we can get the register name, which is SPCRO. It also provides information on how to manipulate the 8-bit register to control the functionality and also configurations. Now, in addition, there is another section that contains a summary of all the register, which is very very useful. And this section is the register summary. And you can see here it provides the memory location, the name, and the parameters associated with each of the registers. Now, we must be able to access all these registers to enable us to control microcontroller functionality and also configuration. Hence, our next task is to figure out which C instructions we need to implement and develop to access all these registers. Okay, so how do we go about accessing the registers? So we have here two lines of code. The function of the first line of code would be to assign to sample 1 the register address. So in this case will be 04. The purpose of the second line of code will be to allow sample 2 to access the memory location of the register defined by sample 1 and be able to look at the data and modify the data. So sample 2 will have access to read and modify the data in the register defined by sample 1. So let's dissect these lines of code. Line 1 defines a macro named sample 1 with a value 04. So sample 1 has the value 04, which is going to represent the memory location of our register. Now line 2 defines another macro named sample 2. Let's analyze it by parts. First we have the volatile word here. The volatile qualifiers ensures that the access to this register are not optimized away by the compiler. We want to make sure, when dealing with registers, we want to make sure that the compiler doesn't do anything to us. Line number 2. This declares a pointer to an 8-bit unsigned integer. So if you have a variable and you want to assign it to be a pointer to an unsigned integer, that's what you put in front. So now why are we doing this? Now sample 1, here sample 1, which is 04, is used as a memory address and it's casted as a pointer of type volatile unsigned integer. So what we're doing here is we're converting the sample 1 into a pointer to a memory location which is 04. And finally, the asterisk operator dereferences this pointer, allowing sample 2 to read from and modify the contents of the register that is pointed by volatile unit 8 sample 1. So let's try a different view to clarify this a little bit. So as I noted, this first statement, what it does is the IO base has a value of 04. Now let's look at the second statement. This portion here, the volatile uint t, casts IO base as a pointer of type unsigned integer. So this makes this a pointer to an unsigned integer. And now the asterisk, this allows you to read or modify the contents of the memory locations by your program. So I let this up for a couple of seconds so you can digest what I'm doing. Okay, so let's look at this matrix that I put together. All this information, I got it from the data sheet that I showed you where it came from. So the data sheet had the addresses, the names, and the name of the control register. So what I added is on the left hand, I added the function. And what I noticed was that the memory locations were 23, 24, 25, and that grouped the microprocessor functionality very nicely. So the next thing I did is I created another column, which was the C code to access register. And I basically used the same technique that I just showed you for coding. So I had defined an IO port B base, because this is pin B, 023, which it comes from the data sheet. And then I define a volatile, and the thing I did here is I said IO port base plus 0. So this defines the memory. So I have the initial memory here, 023, and then what I do is I notice that the next variable is going to be 24, 25 in consecutive. So what I did is IO port by 0, that would be pin B. Then we have the next is DDRB, and this is going to be IO port base plus 1, which is memory 24, and this plus 2 is memory 25. Now each time I had a different function, I started by defining IO port base and the number, and then I just added to the IO port base for that function. So let's look at, so this I continue to get information from the data sheet. So when I'm done with all this, I'm going to be able to trace all the information I have in my framework, in control framework, to the data sheet. And let me see, and the C code to access the register, it's going to turn out to be the code that I'm going to use to implement my control framework. So I'll start reading this so you kind of get an idea of the amount of registers that we have. So we have the general purpose IO register, then we have the EEPROM, and the 8-bit timer controller with PWM. Now we have the general purpose register, SPIs, analog converter. We have the PM power management, system controller reset, the bootloader. CPU core has stuff like stack pointers, Watchdog Timer, a system clock, power management again, system clock. So I just follow every register and added the code here. So later on, I'll show you how I implement what's on the C code access register. So here we go again, the 16-bit Okay, so now we're going to physically create the control framework. The control framework will be implemented as an include file, which I'll call it framework.h, that will include all our programs, that will be included in all our programs. The source code is generated by extracting the contents from the column C code to access register, like I noted, to prevent any naming conflicts with existing development environment. the parameter names have been modified by adding an X in front of each parameter. So here you have the framework, and again, all this comes from we extracted from the C code access register that we developed. And then one of the things I did, in the left-hand side column, I had the description, and I went ahead and added that as a comment. So we have IO port B, and then we have the IO port base, which is hex 23, like I noted. And then pin B, they had pin B only, but I added an X on the back. And then I have here 0 plus 1 plus 2. Then I go to IO port C. So now let's go to a exercise which shows you exactly how I did this using the Atmel Studio.
Okay, so I'm going to create the header file for our control framework. I'm going to use the Atmel Studio. The reason I'm doing through this method is so you get an idea of the Atmel Studio and how good it is, and you can download it from the Atmel webpage. So now we're going to do the file, new project. It's going to be a C executable. We're going to call it Presentation3. Select the device family, which is the ATMEGA, and our chip is the 328P. We go OK. So this created the project. Now we click under the Presentation3, top of the file, and then we right click and we say add new item, and then this gets us we're going to use a include file, which we're going to call it layer 1.h. So we say add, and then it creates the header file, and you can see it right here. You have main here, and you have the layer H. So then we get up here, and I am pasting the whole thing because I already copied it from the from our C code to access register that we created. So I organized it. I put the IO ports, and then we have the IO port base that we had before, and then our code. Then basically what we had on the left hand side, which was the function, I put it in as a comment. So IO ports, interrupts, external interrupts, 8-bit timer, and so forth and so on. So now let's go back to main. And this is how we would use it in a regular program. So we would do the pound include, and then we would have to find our layer 1.h, and there we have it. Now let me add something. Oh, one item that I forgot to note was that for all the parameters, I did put an X in front, PX, pin B, for example. And the reason is because the ATMEGA Studio already has done this work for you, but I decided that I want to use my own, so you guys get an idea where things come from. So, for example, here I can do X pin, and then we have, for example, pin B, and then I could set this to a 0, which means that it's going to be, sorry, 0. Sorry about that. Which means it's going to be all inputs, and I'll show you that next lecture. That's what we're going to talk about. And also I would like to show you that you can do the pin B, and it shows up, and I'll set this equal to 0, and these two things are exactly the same, the X pin 0 and the pin B, I'm sorry, X pin B0 and pin B0. So we can build a solution. And it gets here built success, 0 failures, 0 skipped. So anyhow, here this gives you an idea how to write how to start a project, how to add a include file, and that so that concludes this particular exercise. So let's complete this by going through a summary of what we've discussed today.
Okay, so the summary for today. Today we talked about the system architecture. I showed you what the system architecture is going to look like, and also it's going to be a roadmap to the future presentations. And I also developed the control framework, which is which allows us to access all the registers in the microcontroller. And I also showed you how I went about developing it. Well, I hope you've enjoyed these presentations. In the next presentation, I'll start getting into a layer 2 of the architecture. Thank you very much.